Section 10.12 is called Simplifying the Equivalent Circuit. I really like this section. You probably won't, but we're going to take that rather complex figure that we explored in Section 10.8 of the equivalent circuit that's got all the additional components to, you know, allow for the winding resistance and the core losses and all that sort of stuff. And we're going to simplify it. And when we get done with this, we're going to find this really simple model of this transformer. And you might say, well, why didn't we start there? Well, we could have, but you wouldn't understand why the simplicity works if you hadn't gone through the complex stuff. So let's look at this and step through it. So Mr. Wilde tells us that this equivalent circuit that we looked at in figure 10.8, it's really too detailed for most of the things that we want to incorporate into our thoughts in terms of a transformer. So we're going to go through this process and we're going to simplify this thing, okay? And let's see, how does he go about that? Well, all right, so we had this from, you know, back earlier, you know, we looked at this part of it and, you know, we looked at all of these portions of it and so forth and so on, right? So we understand, you know, where all that's coming from. Now, let's fast forward through here to figure 1020, which is on our page number 209, okay? And so here's the complete equivalent circuit of a transformer under no load. No load's connected to it out here. Okay, so then we're going to look at it at full load, and then we're going to come up with this really neat, simple model that summarizes all this stuff for us. Okay, so at no load, I2 is 0, right? There's no current flowing here. There's no load for it to flow through. And I sub 1, and so is I sub 1, because we're saying that this is an ideal transformer, right? So if that's an ideal transformer, then, you know, there's no current needed to flow through it when it's not loaded, okay? Because, you know, for all the reasons we talked about earlier, right? I can't go back and like reteach this, can I? All right, so, you know, consequently, only the exciting current flows through R1 and XF1, so only the exciting current is flowing, you know, this amount of current. And that's all the current here because it's not loaded. And these impedances are so small that the voltage drop across them, okay, so the voltage drop from here and the voltage drop from here, they're so small that we can basically ignore them. Furthermore, since the current in R2 and XF2 is 0, we can really just negate or just forget about all 4 of these impedances, okay? The turns ratio is N1 over N2. For this one, we're using a very simple, right? Using 1 as the turns ratio to keep things simple. So what we have, what we are able to migrate to is this idea that the N1 over N2 is obviously equal to the ratio of the primary and secondary voltage. You know, it's equal to this, EP over ES, and that's measured across the respective terminals. Okay, and so what we can do, he tells us, is we can view a simplified circuit that is no load representation is shown here, right? Since there's no current in these, we don't really need to account for them. And same thing on the other side, you know? So we don't have to account for them. So we have this ideal transformer, and then we still have this magnetizing current, and you know, we know the reasons why, right? Hysteresis and the resistance. And so anyway, we have to account for that, but otherwise we've simplified this greatly. All right, so that's no load. Now, at full load, let's see if I get this right. Yeah, here we go. Full load, a simplified equivalent circuit of a transistor at full load. At full load, the I sub P is at least 20 times larger than the I sub O, you know, that was going through here. Okay, so if that's the case, since it's 20 times larger, we can basically neglect the I sub O. I don't know what I'm doing with that. We can basically neglect the I sub O because it's so much smaller than the I sub P on the loaded transformer. And you know, we can just basically do away with that whole parallel branch. And that's what we end up with this simplified equivalent circuit of a transformer at full load. You know, we got this and this and this and this, and we eliminated that branch. Okay, now, new equations pop up. He says this simplified circuit may even be used when the load is only 10% of the capacity of the transformer. So this is a valid thing to use even if the load is only 10% of its capacity. We can further simplify the circuit by shifting everything to the primary side, and we learned how to do that in you know, the earlier sections in section 10, 910. And when we do that shifting, you know, when we do that shifting from the primary to the secondary side, we move, excuse me, secondary to the primary side, we move everything to here, right? And we've got the A squared part of that, right? So what's this? A squared, okay? And so when I do that, I end up with this, okay? All right, so, you know, I've moved everything over, and you know, now I've got this circuit. Why do we want to do that? Again, this gets back into a circuit that we can solve, right? When we shift these things over, we have techniques that allow us to solve this. And then we see this equation 10.9 that says R sub P is equal to R sub 1 plus A squared R2. Okay, we okay with that? And then reactive portion is XF1 plus A squared XF2, this guy, all right? And so that's equation 10-10. So this is the total primary resistance here. This is the total transformer leakage reactive on the reference to the primary side. And then if we want to get the total impedance, the Z is equal to the R squared plus or minus the X squared, right? You know, back from ancient days when we were just learning all this stuff. Or a better way to write that is the total transformer impedance is equal to the square root of R plus X, and that is our equation 10-11. Okay, ZP is one of the most important parameters of any transformer. It produces an internal voltage drop when the transformer is loaded. Okay, it produces an internal voltage drop when the transformer is loaded. Okay, I hope this isn't messing us up. There we go. Okay, so transformers above greater than 500 kVA possess a leakage reactance, X of P, that is at least 5 times greater than R sub P. In such transformers, we can basically neglect the R sub P as far as the voltages and currents are concerned. Asterisk right by that, and I'll read that to you down here. He says, from the standpoint of temperature rise and efficiency, R sub P can never be neglected. All right, so, you know, if we're talking about that primarily, then we don't neglect that. But anyway, since the X sub P is he says 5 times the R sub P, you know, we can neglect that. And the equivalent circuit is thus reduced to a simple reactance X of P between the source and the load. Okay, so I kind of left off a thing here. Okay, 1024. I don't see that on here. I see 1025. I don't see 1024. But anyway, he says, I'll go to 1024. It says the internal impedance of a large transformer is primarily reactive. Okay, so this is 5x this, which leads us to 1025. Okay, and there we go, right? The equivalent circuit is thus reduced to a simple reactance, X of P, between the source and the load. And it is quite remarkable that that figure 10.8 that had all those components in it can be reduced to this simple reactance in series with the load. Now, without going through all that heavy lifting and all that stuff we grunted out in the earlier sections, you know, none of that would make sense. You know, somebody could just, you know, spring this on you and you could, you know, look at it and go like, okay, that makes no sense. But now we get it, right? We get all this stuff. We understand where it comes from. You know, and here's something, you know, in most instances, we can use as a model for circuit analysis. And, you know, maybe think about that in terms of, you know, plugging this into, say, a multisim environment and using that as your model as you're doing circuit determination. All right, so that takes care of 10, 12.